Right, so colleagues who are online, we are going to delay the start by a little bit. Looks like an hour isn't enough for all of us to go out at once and get lunch. So we'll start at 1:45 instead of 1:30. So another, I guess, 10, 12 more minutes. So please stay on if you want. Paul says it's, like what is faster? No, it's supposed to be an hour fast or an hour slow. 3 minutes fast. Okay. 2 minutes fast. All right, what the hell? We'll start. Yes, Huda.
There's a comment that there's no audio on the live stream. Is that intentional?
Yes, during there'll be audio when people are talking.
Okay. All right. Okay, so let's turn the audio on.
Yeah,
and
I just turn it on.
Okay. All right. So let's get the proceedings underway again. The second of 3 teams is about to start. So let me just hand it over to Lucia and get going. And again, questions are welcome in the middle. There's time for questions in the end as well. And people watching online, if you have questions, please type them in, and we'll try and keep an eye on the chat stream to see if we need to interrupt the speakers with your question. Yeah.
Okay. Good afternoon. I am Lucia Specia, and we are grounded sequence to sequence transduction team, or for short S2S, in case you can't read that. Thanks, Yanda, for teacher. And we're very grounded. In this picture, you can see the team a little bit better. As undergraduate students, we have Alisa Ostapenko, Carl Oligan, Jasmine Lee. As graduate students, we have Andrei Libovici, Ramon Sanabria, Shruti Palaska, Niels Kosenberger, Amanda Duarte, and Ozan Chalayan. And as senior researchers, we have myself, Florian Metze, Loic Barreau, Desmond Elliott, Josiah Wang, and Pranava Lancaster. We also have 2 graduate students who joined remotely because they couldn't be here, Spandana Gela and Tragla. Let's start with the motivation example. So if we, as humans, see this sign at Edinburgh Airport, we are most likely not going to think that it's telling us to sit on that big ashtray bin. We can do that because in addition to the text, we see many other visual inputs, signals there. We see the shape of the box, we see the cigarette butts on top, and so on. However, our language processing applications mostly ignore these additional input signals. Therefore, it's not guaranteed that if we give this sentence to whatever system, it will be able to get the correct meaning of the ambiguous word there. So more generally, as humans, we interact with the world in multimodal ways, and language understanding and interpretation is not an exception. So we think, and this is what we wanted to do with this workshop, we think that this multimodality should be brought to computational models as well. And with that, we can have richer context models for language tasks, and we can have grounding of language on different modalities. And this is true for a wide range of natural language applications. And the reason we chose sequence-to-sequence models here, and in particular sequence-to-sequence neural models, is because they offer a very convenient approach, which is very flexible for different tasks and different modalities. And you see more on that later. So there has been some previous work showing that multimodality is promising for language tasks, or primarily language tasks. One such an example is that of multimodal machine translation, where the task is given a description of an image. We have to generate a translation of that description. And the question is, if we use the additional modality, the actual picture that corresponds to the description, can we get improvements in translation quality? And these are some results from the latest edition of a shared task that we run on this task, on this problem. And these are ranked participating systems according to human evaluation, where greenish means a multimodal system and purple means a text-only system. And as you can see, the 2 top systems there are multimodal, and they're significantly better than any other system. And another interesting thing to highlight is that if we take 2 systems that are pretty much the same, except that one version of the system uses a second modality, which is the images, that system does significantly better than the text-only counterpart. Another promising result comes from speech recognition. This was a previous work where the task was to do ASR using transcripts or using videos and trying to do the transcript of those videos on 90 hours of how-to videos, which is very similar to what we're going to be showing you later in this presentation. And this was done using features, object and place features from pre-trained networks to predict or to classify objects and places. And these features were used to adapt the two main components in an ASR system, so the acoustic model and the language model. And they showed improvements, the use of these features showed improvements for both components and also for the combination of these two components, with a reduction in word error rate of almost 2%. And when the authors inspected these results, they found that the improvements made sense because most of the improvements came from a certain type of video. So even though on average it's only 2%, if we look at particular types of videos that are, one would say, acoustically harder, because they're outdoor scenes and have background noise, for those videos improvement was much higher. These are just some examples of those types of videos. For example, a scene where you have a plane in the background with a lot of background noise. So even though we've seen improvements for these two tasks, there's still a lot of room for work to be done in multimodality for language tasks here. And more specifically, the data that has been used so far is relatively small, especially for MT. It's also very easy to translate. It's just simple, short descriptions of images. Only a few modalities have been used, especially the visual modality. We've only used static image, either a picture or a couple of frames from an entire video. Only these two tasks had been addressed so far. And they have been addressed in isolation, so there is nothing to be said about learning sharing presentations across multiple tasks. And it's also not very clear in general where the improvements are coming from. So what we wanted to do, and I can say that we partially did, in the 6 weeks was to, well, first get more data, include more modalities and more tasks, and hopefully this should lead to better models, better representations, and a better understanding on the tasks and their performance. So before I move on to the actual topics that we covered, just 2 slides on our data set, which is something we started building before the workshop and we're very proud of. Our main data set, I should say. This is a 2,000-hour of video and audio data set. These are how-to videos, or videos on how to do a wide range of things, from cooking to changing or fixing a tire. And this data set, even though it's been used for pretty much all of our tasks, we concentrated on different subsets of the data set depending on the task. So we have one subset that is shared across all of the tasks, which is this 300 hours, where we have the videos, we have the segments of transcripts of human transcripts from this video. We have the audio segments aligned to this text segments, and we also have translations for that. We have a slightly bigger, also clean version of this data set that we've been using for ASR, and for that it's a slightly different segmentation. It's a segmentation that makes more sense for ASR. In all cases, we have shared splits and held out data. We also, for the data set, like I said, we have the ground truth captions that were given by humans. We have a lot of metadata that can be useful for this or for ours or other tasks, such as visualizations, the person or the user who uploaded the video, tags, and so on. We have one particular type of metadata which is very useful, which we've been calling video descriptions or summaries or teasers, as you see later. And this is a very short description here in green, which the authors of the video or the creators of the videos entered. And it's basically a teaser about the content of the video. We also, so we have this for the entire set of 2,000 hours of videos, so 80,000 of this. These videos, like I said, cover a wide range of topics. And for a subset of 300,000 segments, where a segment is pretty much a sentence, we have translations into Portuguese, which have been done by humans.
Very quick question.
Yeah.
How does that last bullet relate to the 300 hours for MT?
So the 300 is a key number here. Refers exactly to the 300 hours that we have up there.
So it's roughly 1,000 segments an hour.
Yeah.
So it's 3.6 seconds per segment.
So just so you know a little bit more about the data set, I'll play a short video. They're all very short, a couple of minutes
When
max.
you're selecting a teapot that is glass, it's always best to go with the best brand because glass already is very fragile. If you want to buy something that can withstand the heat without worrying about pouring warm water in there, prepare the teapot. This is a Jena glass teapot. This teapot is amazing. You can put it in boiling water, then put it in the freezer, and it won't break. It is also handmade where the spout, when you pour the tea, is a dripless spout. You'll know what I mean in just a second. This is the best type of teapot if you're trying to brew.
Okay, that's enough. So if you're reading that, you see that the transcripts are pretty good and they're aligned, and we have translations that align very well with those as well. And you see that there are different things happening in the video. You had the person talking a lot of the time, well, all of the time, but you also have the camera zooming in different objects and the person, and normally the things that the person was mentioning, but not always. So this is the big picture that you see a number of times in the presentation today. And this was a way we found of putting everything we wanted to do together. Things to notice here is that we have, of course, multiple modalities. So we have the text modality, we have audio modality, and we have the video or even the images coming from different frames. We also have different tasks that we can do with data coming from different modalities. We have translation, we have ASR, and we have summarization. And we also have translation from the text and from the audio directly. So the idea with this big picture is that one could use inputs coming from different modalities, one or more of these modalities, to generate one of the different text output tasks. And another thing to highlight is this pinkish bit in the middle, where we can have representations that are shared across tasks, and they can be used for different types of applications. And the final thing to notice is that everything is done using sequence-to-sequence models.
Lucia, just to clarify, it's
Yeah.
obvious to me what transcription is, and I think it's obvious what translation is. By summary, you still mean the description of what's in the video, not a summary of all the transcripts of the video.
Yes, that's what we mean. And when the summarization team talks about the work, they will clarify that. Yeah. Right, so in the rest of the presentation, this is the structure that we'll follow. The three first topics there are sort of tasks or applications. So we have ASR and spoken language translation. These are together because they share a lot of the models that they use. We have text summarization, which is a slightly different version of summarization. We have region-specific multimodal machine translation. And then the two last items are on the representation learning side. And we have two main ways of doing that, using either multi-view learning or multitask learning. And before we go to the specific groups, I just wanted to highlight some of the main things that we produced or found in the work in 6 weeks. And I limited everyone to only have 2 bullet points there, otherwise we'd have many more things. So these are the top highlights. So from the ASR and spoken language translation team, we now have multitask learning approaches that have proved to improve on both tasks. And they've also found that one-to-many models, in the sense that we have one encoder and multiple decoders, they generalize better than the other way around. So multiple encoders and, and one decoder. From the summarization team, we now have, for the first time, models that can successfully generate teasers for videos. So the summary comes mainly from the text and not from the video itself, but the video supports that process. And this multimodal approach to summarization, where action features are used as visual input, outperform text-only models. From the region-specific multimodal MT team, we've developed supervised attention models that can successfully ground words in the source language to regions in the image. And we also have models, a number of models that can explicitly, can use this and other types of grounding to improve machine translation quality. From the multi-view learning subgroup, they've implemented and explored a number of types, a number of multi-view learning approaches, mainly canonical correlation analysis and versions of this approach, which are deep and generalized canonical correlation analysis. And they found that there was a high cross-view retrieval when they're building presentations using multiple views that correspond to multiple modalities in some cases. So using these representations, they were able to retrieve similar data in our data set. And they've also used this to improve different tasks, MT and ASR, with promising results. From the multitask learning group, they found that they developed a single framework for multitask learning that can work with multiple inputs and outputs. And by inputs and outputs here, I don't mean only the ones that I showed in the big picture, but additional modalities such as generating videos. And they came up with two main new models, one multimodal shared recurrent space model and a multi-projection network, which they'll cover later. And in general, with the data set and the evaluation methods that we propose or that we use and propose in this 6 weeks, we can do a lot more work. So we have now data sets that can be shared across a number of tasks, and we have best practices and metrics that can also be used for that. And finally, we have our code base, NMT PyTorch, which already existed, had been developed at Le Mans University, but we added a lot of code to it, and a lot of models. These are the new things we added. So different types of data loaders for different modalities, different layers for different types of encoders and decoders, such as auxiliary feature integration, encoder-decoder, hierarchical attention, co-attention, supervised attention. We have video encoder and decoder that were not there. We have sequence convolutions, latent recurrent space layer, and so on. We have a number of models that make use of these layers. So we have models for ASR, for spoken language translation, for multimodal MT, for the multiple projection network models. And in terms of multitask learning, we have new scheduling approaches and various combinations of encoders and decoders, one to many, many to one, many to many. So this is roughly what we try to follow as a schedule. So we have, like I said, the 5 teams talking about their specific work. We have a break in between. If you have questions, we mostly don't mind that you ask them right away. But if it's a more philosophical question, if it's not a clarification question, then we'd like you to ask at the end of each of these short presentations. Each presentation will last about 20 minutes, and we have about 5 minutes for the question. So, and we still have some time in the end for question. Yeah. Okay, so we start with the first team talking about speech recognition and spoken language translation.
Thanks. Speech recognition, spoken language translation is mostly going to be presented by Ozan and Ramon. The team is myself, Jindrik, Ozan, Ramon, and Shruti, and I'll really only sort of say hi and introduce the task. This is, I guess you can see which path we're following here. We take the speech signal and we take a keyframe from a video. So we take one keyframe for an utterance of a speaker. So this is really just a single frame of the sequence, so we're not using all the capabilities. And then we're generating either a transcription in the original language or a translation into a new language using a sequence-to-sequence model. We've shown that this works in the past. Just to recap, in how-to videos, speech and visuals are often highly correlated. And you can imagine that if somebody says, start by loosening each bolt, then locate the jack and lift the car, that if you can observe these objects and these actions in the video, then this is highly informative both for the language model to tune to this domain, but also for the acoustic model to say, oh, this is happening outdoor, we're expecting these types of noises, or this is likely a female speaker, indoor, clean. And so we're exploiting these effects. in the past, we've already run a number of experiments on this data set using slightly different setups. We've had success with 90 hours of training data in HMM models. We've run CTC models on 480 hours, and we've also run language model adaptation on 480 hours of data. Now, for this workshop, we're going to present results on 300 hours of data mostly, which unfortunately is not compatible with the previous, not exactly compatible to the previous results, but we picked it so that we have also translations for the 300 hours of data into Portuguese. So the speech recognition and machine translation experiments are going to use the same data set and also the same vocabulary of 5K sentence piece tokens. So going forward, most of the results that you'll be seeing will be on the 300 hours of training data and on say two different test sets, either dev test as we call it, and the CBO5, the validation set. And we're getting word error rates just below 20%. Using ESPNet, 23% using ESPNet using word units rather than character units, and also 23% word error rate using a small word-based baseline using NMT-Pi, and 19.6% word error rate using a word baseline in NMT-Pi, which is sort of a comparable to, if all things are made comparable, ESPNet and NMT-Pi tend to give us pretty close, pretty very similar results. With that, I hand over to Ozan for automatic speech recognition.
Hello, everybody. I will give the automatic speech recognition part, and then Ramon will continue with the spoken language translation experiment. First of all, I'd like to give a very short introduction to our baseline for ASR. So this is the small model that Florian mentioned about it. So we have a modest encoder for the speech and a two-layer decoder which used the GRU RNN units. So this model has almost 4 million parameters, and we obtain a word rate of 24 on the test set. But if we were to increase the complexity on the encoder side, we are almost at the same point with a comparable ESPNet baseline. But we decided to go with this small model because of fast experimental turnaround time, so that we were able to train as many models as possible. So for multimodality, the initial motivation that was mentioned by Florian is that the speech and visual in this dataset are often highly correlated. So the idea is, first, can we improve the language modeling ability in the decoder by somehow shifting the output distribution by conditioning it over visual context? So here in this first part, we will mostly use global visual features, which should be representative of the visual context of the video. And the second experiment will be about multimodal attention, where we will be using temporal visual features, which are not a single visual vector, but a collection of visual features extracted from the whole video. So as per the video features, we use this action level recognition network, in which the network was trained to do a 400-way action recognition. We can see some examples here. There are pull-ups, push-ups, climbing, playing instruments, and so on and so forth. So what we are doing to extract the features is we feed the videos, and we extract one feature vector per 16 frames, which comes around, and so this results to have almost 2 feature vectors per second. And we extract the features at the penultimate layer of the network, and we obtain 2000 dimensional features. So one thing that I should mention is that although we are working on the 300 hours dataset split, which contains many segments extracted from a single video, for this experiment we used the whole video to extract the features. So we are actually providing a context that is consistent across all the utterances extracted from a single video. So first we tried some simple decoder side multimodal integration. So this is the like detailed version of our architecture. So our decoder is actually what is called a conditional GRU. So we have 2 layers of GRU, and in the middle we have a feed-forward attention mechanism. So the first experiment was to take this collection of action level video features, apply min or max pooling to reduce them to a single visual vector. We normalize the norm, L2 norm, to be 1 on these feature vectors. And then we start experimenting with first concatenating them to the target embeddings. Second, adding them to the target embeddings, and finally, we experiment with also element-wise multiplication. So these were already sort of explored in multimodal machine translation context last year, WMT. So we wanted to see how does this models perform in the context of ASR. So basically, the results are a little bit better than the baseline ASR, but the differences are not that promising right now. But all the average pooled, the average pooled feature vector seems to work a little bit better than the max pooled version. But there is no clear conclusion here for the sequence-to-sequence decoder-side integration. I think we need to experiment with bigger models and also different features like object-level features and also scene-level features and hybrid features to see how these models behave in those regimes. And also we are right now, there are some experiments ongoing for the encoder-side adaptation instead of decoder-side adaptation to ground the visual context in the encoder level with speech instead of pushing the integration in a late phase of the network.
Quick clarification. Do we need to understand these conditions, average cat, sum, whatever, or it's not important?
So the concatenation, sum, and multiplication interactions.
Ways of combining the
Yeah, these are like average pooling or max pooling and some concatenation.
Yeah, okay.
Sorry.
I have a quick question also, but it might be for Florian. So why do visual features improve generative acoustic modeling? That's counterintuitive to me.
Why does it improve the acoustic model?
Yeah, so you said an HMM, so I guess a generative acoustic model.
Yeah.
So is the idea that I would pronounce I would pronounce a word differently because I don't know, it's route versus root or something? No, that's not a bad example.
No.
Why does the visual feature help?
So we've run diagnostics earlier, and it shows that really the challenging the acoustically hard videos to improve. So when you're outdoor, like when you're repairing a car or when you're taking a train, there's videos to show you how to take a train.
Oh, I see. It's predicting the train noise.
Exactly.
Yeah. Okay.
That's what seems to be happening.
Yeah.
So what that sort of was accurately recognized because of the action mechanism-based models. This is because you introduce the features which can support characterized action.
Yeah.
So it means that we expect that the speech recognition results, especially for the action-related parts, accurately recognized.
Yes, so we should. That's why we should also explore object-level features, maybe which are much more fine-grained. But it's true that all these how-to videos are sort of much action-related. So if the CNN can capture not only these 400 different types of actions, but all sorts of interactions between them, this may be useful. But I think the best way is to use also other types of visual features.
Actually, you have never seen the comparison between approach by approach, what types of words can be recognized better than others. You have no tables, confusion matrix, or
no.
Yeah.
So for the second part, we experimented with multimodal attention, where we add another attention mechanism in the decoder. So we still have the attention over the speech, but we also add an attention over the visual features. But we also add a third attention mechanism on top of this modality-specific attentions, which we call hierarchical attention. That will sort of learn how to gate these multiple modalities during decoding. here we have two variants. One is to use the action level video features as they are, and the other one is to encode them with an RNN as well. So once again, the results are right now not so conclusive. If we pick the average pooled versions of the previous experiments and add the action and the action plus GRU, first of all, the action plus GRU sort of performs very badly compared to the other ones. We will see what's the reason for this. But we think that the average pooled and average summed and action level networks should be further explored for the same reason that we will see right now. So here, I hope that you can see the attention distribution for a sample in the test set. So here, this is the attention over speech. So once we decode the target tokens on the y-axis, we see how the attention is focusing on the encoder speech encoding state. So here we compare the action level features with the other experiments where we encode the action level features. So basically two completely different systems trained with different types of encoders for the video level features, but they almost consistently produce the same attention over the speech. But if we check the hierarchical attention, in the first version we always use the speech modality. So the hierarchical attention learns to not pay attention at all to the visual features. But if we encode the action level features with an RNN, everything changes. In this case, the speech receives very weak attention. Although the speech attention on itself is good, the hierarchical attention decides to pay less attention to the speech features. And what happens on the video level attention? In the first part, we see that for some of the video features, they receive the consistent attention for all the tokens, but the attention is sort of dispersed. But if we encode the action level features, we have, although the network decides to pay attention to this modality, inside we don't really have something meaningful. It's all uniform. But for another sample, we see that in the second part, the network decides to attend to the final part of the video and just ignores completely the first part of the video. So there's a problem with regularizing this attention. So in overall, the transitive attentions are sort of the same. The modality that's receiving the attention shifts between these two models.
Well, hello everyone. I will present a spoken language translation. In this task, what we are going to do is build systems that get a speech as input and translate this speech to another language. More concretely, we will feed English and we will try to translate it to Portuguese. So, during this project, we found 3 questions that we tried to answer. The first one is, can having another language or feed another language to the model improve ASR? The other question that we try to solve or to improve is, can we improve current SLT approaches? And the last one is, having speech as an extra input of a machine translation system, can we improve machine translation task? So for solving or trying to solve these questions or to answer these questions, we built 3 models. We call it many-to-one, one-to-many, and one new hierarchical auxiliary supervision. So let's take a look to these models. This is our baseline. It's exactly the same thing that Ozan presented in ASR, but the only thing that we change is the last part, where instead of trying to predict English, we will predict Portuguese, feeding exact same thing, feeding a speech into the model, English speech. So these are the results of the baseline. The blue bar is the SLT baseline, is the architecture that you have behind this graph. And then the cascade model is when we take an ASR system, we train it just for ASR. We take a machine translation system, we train it only for machine translation, and then we pipe the result of the ASR to the machine translation system. So ideally, our models will be better than the blue one, and our final goal would be to outperform the the red one. So this is our first model, and is many to one. So the motivation of this model was to build one decoder, one more generalized decoder, a decoder that can accept encoded speech signal and text signal at the same time. To train this model, we had to train it in a multiplexed way. So for this, what we were doing is basically taking a batch of one of the tasks, let's say a speech to Portuguese. We trained with this batch. Then we take a batch from English text to Portuguese text. We train it with this batch. We train it with two types of multiplex training. The first one is alternating the batch. So one batch will be for one task, another batch will be for another task. And the next one, it was applying some probability. We sampled across all batches for one task and for another task with 1% of probability. Then we have a variation of this one. If you notice, we have two types of attention, one for each task. We also have another variation of this model that we have the same attention mechanism for each of both tasks. Let's take a look at the results. So here we have in the right part we have the SLT performance, and in the right part we have the machine translation performance. Both of them are blue score, so bigger blue score is better. We can see that for SLT, we have two models that outperform them. So when we apply a 0.7% probability for sampling batches for one task of machine translation, it's not helping. But sampling 0.7 of speech batches, of SLT batches, we get some improvements there.
Excuse me, this is a 4-gram blue. Blue is how many grams?
How many?
4 grams.
4 grams.
Okay.
4 grams, correct.
But
So
you have only one reference. One reference translation.
Yeah.
correct.
A single reference.
Single reference.
Reference, correct. So we can see that none of the approaches help machine translation, but since the problem that we want to solve is spoken language translation, for now it's okay. So our next model is the one-to-many. In this model we have just one encoder and several decoders. Our goal here was to build a more generalized encoder, and with these two decoders we will help to have a better representation for both tasks at the same time. In this case, what we could try is to, instead of scheduling, just performing back propagation from one batch or the other, what we do is just feed the same the speech, and then we can get two targets, and then average both losses. Let's look at the results here. So in SLT we can see that all the models that we tried outperform the baseline for SLT. In the right side we have word error rate, so in the right side lower is better. In this case, the best previous many-to-one model is 29.5, and all the one-to-many models outperform the many-to-one model. You can see the best one is alternating. And also the interesting thing here is that SLT also helps ASR performance, which is also what we need. And finally, this is our last model. So a priori here you will see the same model as we discussed before in the previous slide, but what we wanted to do is have a type of hierarchical multitask learning. Here our motivation was that we wanted to have an end-to-end model that ground the intermediate representation to English. So note please that when we are testing, we will not take into consideration the decoder of English. So we allow the network to learn some intermediate representation that we don't know what is it, but he will use it in order to finally translate the speech to English, to Portuguese, sorry. Then we can see that is where we get most improvement. So we have, from the baseline, we achieve almost 5% improvement. But the bad new or expected new is that the ASR results were very, very bad. But it's very important to note that we were not forcing that this intermediate representation to have pure English. We just have it as an extra loss. Okay, so finally, for conclude all this subsection, or this section, in multimodal ASR, we got consistent improvements on speech recognition as the improvements that multimodal neural machine translation people got. We want to perform further exploration in using some type of smoothing on temporal domain of the visual figures. And in later parts, I think that now is Yendra team that will talk about summarization, and they have some exploration of these parts. And for spoken machine translation, we interestingly see that there is benefits for spoken language translation and ISR mutually. The one-to-many model seems to perform better than many-to-one model. And finally, the best model that we currently have is hierarchical spoken language translation, which currently we are almost closing the gap between hierarchical SLT and cascade, because we're training more models with more parameters, and this is actually helping us to close more the gap. And yeah, thank you.
Questions for the ASR and SLT part we can take.
So these are the video description research. They are using objective recognition and emotion recognition features, bottleneck feature, what we combined to predict the object, things in there and what's going on. So why you don't want to combine the other bottleneck feature using much more bigger training model like ImageNet or?
We actually want to try them. We had some initial experiments with pooled 5 average pooled features from extracted from ResNet 152, but we only used it to initialize the decoder, and the results were almost the same. So that's why it wasn't included in the
Did you
results.
use something audio event prediction acoustic model?
No.
So just a speech only?
Yeah, for the speech features, we are just using speech features. Yeah.
So in the future, you can combine everything?
Yeah, I think so. Okay. Thank you.
Hello. I will introduce another task we worked on. It's joint work of Florian, Jasmine, myself, Shruti, and Spandana. We call that summarization, but more appropriate term would be a textual teaser generation. We work with the transcription of the videos and the visual information, and our goal is to generate a textual teaser of a video. It's usually a short text of 2 to 3 sentences, providing basic information what the video is about, and it's written in such a way that it should attract attention of people who might potentially watch the video. Yeah, so we use transcription, combined transcription and video, and also we try summarization directly from the video. Unlike the machine translation and ASR, we use the whole 2,000 hours of data, which means 74,000 training examples, because the common test set contains only 150 video, which is not enough to estimate the quality of the teasers. This is an example how the teaser and the transcript look like. The teasers have on average 33 words, and the transcripts have on average 290 words. This one is a little bit shorter. We have video, we have the audio, which we don't use, and this video is less than 1 minute, but on average the video have 1.5 minutes. If we look at the language of the transcripts and of the teasers, we immediately see that whereas the frequencies of the words in the transcript correspond to normal English, And the teasers, there are very frequent words which come from some common phrases in the descriptions. They are printed in bold, and you can see that none of these words, free video, learn, tips, is not even present in the most common 50 words in the transcript. This makes the generation of the teasers kind of easier. On the other hand, it makes some problems with the evaluation, as we will see later. This is an example of a reference teaser and a hypothesis. We can see that the reference talks about learning to play ukulele, whereas the hypothesis, for some reason, contains banjo. If we look at the text, it's obvious that if we do some basic n-gram statistics, the hypothesis would achieve a high score, even though it's not quite correct. So on top of Rouge L score, which is standardly used for summarization evaluation, we introduced another metric which computes the F score over the content words and uses the monolingual alignment from the Meteor score. If we look at the examples once again, if we compute the Rouge L score, we first compute the longest common subsequence, which is in this case the guitar learned about from the game-based free video. We see that this longest common subsequence is 12 tokens. We compute the recall and the precision and an F measure from that, which is pretty high. But if we do our content word F score, what we do is we just first remove all the function words and also the most frequent words which are in all the transcripts. Then use the monolingual alignment that we got from the Meteor, which uses also some paraphrase tables and stemming, and compute the F score over these matching. So now we have only 4 matching words out of 12 or 13 content words and hypothesis and reference. Compute the precision and recall and got an F score. The drawback of the Rouge L matrix is obviously that it is not able to capture proper content. On the other hand, the F score that we use totally ignores whether the generated teaser is fluent or not, but fortunately we don't have any problems with fluency of our teasers. The first experiment we did was that we did simple extractive summarization from the golden transcripts. We just wrote few rules to get the most informative sentence from the transcript. In this case, it was selecting a sentence that contains how to, or the predicate of the sentence contained learn, tell, show, discuss, or explain. If there was no such a sentence, we chose the second sentence of the transcript. We can see an example of such a sentence for the video that you saw. And it's a pretty good summary. It tells us that a video is about making a Spanish omelette, which is probably the information that we might want. And it gets 16 Rouge points and 18 F1 points, which is reasonable. However, if we do a random baseline, if we train a language model just on the descriptions without conditioning it on the transcripts, we can sample very nice teasers like this, but it has nothing in common with a Spanish omelette. It says about playing drums. And this random baseline actually scored higher in the Rouge L score than extracting the most informative sentence. Fortunately, in the content F1 score, it gets quite little numbers. Then we did some experiments with attentive sequence-to-sequence models compared to what is standard in machine translation. Our models are relatively small. We have two layers encoder and decoder with 256 hidden layers. The reason why the model is so small is that we need to fit long transcripts in the memory. This table shows the experiments we did with vocabulary. We tried both using binary encoding and directly the tokens. And it appeared that using BPs is not a good idea. One of the reasons might be that there are virtually no proper names in the teasers, which means there's no room to the BP to do their best job. It also showed up that using really large vocabulary just slows down the training and doesn't bring anything on top of using 20K vocabulary, probably because they were most of the edit words were not frequent enough to learn reasonable embeddings. When we further experimented with the sequence-to-sequence models, we wanted to know whether we need the whole transcript or whether it is enough just to use the beginning of the transcript because the very first sentences of the transcript usually contain all the important information. It appeared that indeed we need the complete transcript because when we used only the first 200 tokens, we get 27 content F points. If we use only the extracted sentence, we get 36 F points, which is kind of interesting because the extracted sentence is almost all the time within the first 200 tokens. So just selecting more cleverly the input and doing kind of style transfer from the extracted sentence to the form of the teasers helps a lot. However, the best results were achieved while using the complete transcripts up to 650 tokens. So these are our textual baselines, and later we did also some experiments with the video features. We used the same action features as was introduced within the AirSal talk. And the first experiment we did was attentive sequence-to-sequence models going directly from the action features, which is one vector for every 16 frames in the video, which gave us 24 content F points, which is slightly better than the random baseline. However, when we applied a bidirectional RNN over the action features, we get decent improvement to 35 content F points, which is similar to using the first 200 tokens as an input. This encouraged us to combine the modalities to use both the textual inputs and the video features. We experimented with similar architectures than in the ASR, which means doing evolution on both the video features and the text, and either concatenating the context vectors or doing hierarchical attention. This brought us a modest improvement over the text on the baseline. The sad thing is that the models were very slow to converge. The plot shows the training time. After 1 day of training, the textual model fully converged. But after 2 days of training, the multimodal model seems to have some potential to grow a little bit. And these results are while using the action features directly. We also tried applying the RNN, which helped a lot in case of generating the teasers directly from the video features. However, these models are actually much slower to converge, and we weren't able to give an improvement from them. But maybe if we let them run for weeks or something like that, we might get the same numbers as with without RNN. So to summarize our quantitative results, we trained some textual baselines. Doing random things gives us 8 F points. The best thing we can do with the transcript is training directly a sequence-to-sequence model, which gave us 47 F points. Surprisingly for us, going directly from the video and not using the text or the audio at all give us also a reasonable result. And if we train our models carefully, we can even get a modest improvement from going multimodal. Now Florian will show some qualitative insights into the results.
Yeah, I want to thank Jendrik for doing the hard work for implementing all this.
I had a question I was thinking about these, so maybe for any of you. In your data set, like the held out partition, the dev and the CVO5, are there videos of types that are not at all present in your training? Meaning, cooking omelets, fixing tires. Maybe there is something about fishing, and there is no fishing mentioned anywhere. Are there any such cases? Is there any, or is your partition always such that there's something in training which is like the thing in there?
Right. So we did not take the topic of the video in account when we created the partition.
Yeah.
And that's one of the things we want to do. I'm going to talk about topics a little bit later and show some analysis of the topics and exactly what you're saying. Remove one topic from the training and see how much this generalizes. That's one of the next things. One of the next things to try.
Some more questions?
I guess we're in the middle of questions.
Okay.
So a quickie, perhaps. If somebody says in the video, "Hey, I'm going to teach you about this, but I'm not going to teach you about the following," because that's a follow-up video, does that confuse your model? Or can you detect that?
Not explicitly.
We didn't check for this pattern. But it's likely that it can get confused, I guess.
A teaser is something very different than a summarization. In the summarization, you want to give the punchline. In a teaser, you don't. If you want to generate clickbait, there's very different strategies from doing clickbait than from getting a useful summary or abstract or something. So have you looked at, if not, what would be a metric be to do better job to tease that out and to evaluate how well you're doing? Because clickbait would be, how juicy is your attraction, how much clicks do you get? In the other case, you want to say how much useful content can you retain.
So how to call this did generate a lot of discussion amongst the group. And in the metadata of the videos, the summary is called the description of the video. And we looked at it and we said, well, it's not really a description because it's clearly the way it's displayed, it's meant to make people click. So we called it a teaser.
I think you're confounding the issues, basically. Yeah. And the metric blur is probably confounding it even more.
But we're using rouge.
Oh, rouge, yeah.
But yeah, evaluation is a challenge here.
Follow-up question. Yeah, the other thing is, in useful summaries, there's also, particularly with video, there's a certain drama to it. I think trailers are a great way of of both attracting as well as giving you a good sense what the movie's like. But it, for example, doesn't extract pieces, and it select suggested pieces that are more of a video production than just cutting and splicing pieces. So I think there is an artistic aspect of it that would need to go into the loss function also. Does anyone here know how Apple generates its moments videos?
Anybody of Apple? Is that an answer or a question?
Just a simple question. Did someone actually look at the final results to see how much of the information is hallucinated versus not present?
Yes, that's now the good part that I get to talk about. So I was interrupted and said, well, thank you, Jindrik, for doing all the hard work and helping about the numbers. But yeah, what does it all mean? What is a Roux score of 40 to 48? What does it mean? That's what I'm gonna talk about.
So I'm just curious, if human beings trying to, make a teaser using the speech recognition result, how good? Have you ever seen that result? So this is because when you try to compare the sentence between sentences, maybe a little bit difficult. Even a human being cannot generate such a nice teaser using speech recognition only, or maybe watching video.
So the ground truth here is human generated. What we did not do is have another human sit down and regenerate the ground truth and say what
from
is
the transcription
right,
only.
what is their performance. So when we started out and when we started planning for the summer workshop, we wanted to look at labeling, crowdsourcing teasers and everything, but labeling video is just very, very time consuming, and even crowdsourcing the translations from English into Portuguese of 300 hours of 400 of this corpus took a long time, so that in the end we decided we want to do summarization, or let's say we want to do something that resembles summarization, but we don't have the time to label data for it. So what can we do? So there are these descriptions that seem to be teaser-like sentences. So let's treat this as a proxy problem. Let's work on this and try and regenerate automatically these descriptions / teasers. More questions? All right. So what does it all mean? Or how does this work? So what we have here is the textual, the transcript of a video, and this is the ground truth, not the output of the speech recognition. And here we have a summary, and so we plot the attention patterns of when we're generating the summary over the words. And also this is a hierarchical model, so we also have the video the model here. We can look at the trade-off between the text path and the video path. Now the first thing that you notice is that when we're generating words that appear both in the transcript and in the description, like in this case detail brush, use a detail brush to do this, then of course the model picks it up and takes it from the transcript. So the model picks up words from the transcript and put them in the summary. You can see that from the attention, and even things like windmill, watermelon, or windmill watercolor painting, things that don't verbatim appear in the transcript, but where the word windmill appears in the transcript, then puts a lot of attention in the part of the transcript where it's getting this information from. So that seems to make sense. It's not hallucinating things out of thin air. For a few other words, however, for example, in this case, there's a professional artist in this free painting video. So this is something that the system generates without the word sequence professional artist in a free painting video appearing in the transcript. And now it's taking it, so you can see the yellow bars here. Now it's putting attention on the action features on the video part. because it sort of learns, it gets the information that this is a painting video from the image. Seems to be easier to get from that part, and then the phrase professional artist in this free painting video seems to be something that the language model just has learned on the training data and just generates without needing more information. So,
quick clarification, is this a training example, I suppose?
I think that's a test example.
Yeah, it's a test example.
So this is an automatically generated gist on the left side.
Yeah. Sorry, this is the output here, and
does that make sense? I mean, for that video, basically, what is on the left side, then basically.
It does. Yes.
Yeah.
Maybe we should have switched the order here. So typical examples are, the reference says partial dentures come in both plastic and metal versions. Examine different types of partial dentures with information from a dentist in this free oral hygiene video. And our automatically generated summary based on text only is partial dentures will help to prevent dentures. Learn about partial dentures from a dentist in this free oral hygiene video. So it gets the words right, but it's not particularly informative, if you will. But it's getting a content score of 47 because it really beats on the right words. Now the two versions of this, the action features only or the action features post-processed by the RNN. The actions only, in this example, it's pretty random, and the action RNN, it sort of cleans it up a little bit, and I find it interesting that it learns about a vacuum cleaner that it uses to clean your teeth. So maybe it gets something, and these things are examples of summaries that give an F-score of 35 or 25.
It does use free everywhere.
Yeah, I mean this is hard-coded in the language model. They're all free. And there's another example, and that's maybe a better one. The reference says stretching out your calves is a great way to alleviate stress and rejuvenate your muscles. Learn a healthy leg stretch from a yoga instructor. The text-based model says, well, stretching is a great way to warm up your calves. Learn some calf raises from a professional Pilates instructor in this free fitness video. And that's indeed what they show in the video. So this is really generated from the context and from the content. And this professional Pilates instructor is something that does not appear in the video, but it's something that makes sense in the greater context. Both the models that only use the images, the image information, they seem to detect something that's called Hatya Yoga and then generate some text around that. So clearly going from the image, from the actions only, probably is not enough, but text-based and in particular the fusion of the two seems to be doing something really useful and interesting. And so this is really the type of model that we have here. This is a multimodal model for which we need to do more analysis. We did more analysis here and showed, if we have those video features, where does it put the attention in the temporal sense in the video section? And it seems to be really putting most of the attention in that part of the video where close-ups appear of, in this case, brush strokes with hands, so where you can actually see actions. So in this video, we have a cut here and we have a cut here, and only in this part do we see actions and movements, and the system tends to put the attention in those parts of the video. Now, there was a question about topics, and so yeah, we've looked at this. We did topic analysis on all our 80,000 videos, and so we know what we have. And another baseline that we could do would be to say, well, what if we just take the next neighbor? We have a video, we know, we do a topic analysis, LDA analysis of it, and we just pick the nearest neighbor based on topic analysis and take the summary for this video as a description of the original video. And so here's a typical example, again, the partial denture version. And we find another video that also talks about partial dentures. They have very similar descriptions. However, in terms of these metrics that we're using, the Rouge L and the content F1, they don't look too good. They perform similarly to our rule-based baseline, and worse in content F1 than in all our sequence-to-sequence model. And the reason for that is that there's a large number of videos that, at least in our best effort implementation of the topic model, we're getting really, really different descriptions. So one video describes the bra, and another video that's the closest in topic space then really has a summary that says, don't wrinkle your suit right after ironing it, and learn how to hang a jacket. So clearly here, just picking the nearest neighbor is not something that works well on this corpus. So I think these are very exciting and very encouraging initial results. In particular, it seems that the fusion of audio and visual seems to be creating something new, even though we don't see that much of an improvement in the Rouge score yet. However, what we are doing still, all of this took a lot of time to get up and running, is we try and incorporate the context vector as an additional feature into the summarization, because we think that might help. We're looking at things like multi-document summarization. Can we generate descriptions not just for one video, but for two videos? And we train systems on those, but we don't really have a good way of how to evaluate this, and we don't really have a way of making sense of that. Now we're getting a Rouge score of 52.1 versus 53. We thought maybe we could use it as a form of data augmentation, so that's still ongoing. And we also want to look at things like discriminative summarization to sort of look for better use cases and say, oh, can we generate useful descriptions that say, this video shows this video shows this, and this is how the two videos are different, or this is how the two videos are same. So we have a few ideas, but we haven't gotten around to implementing this as part of this workshop. So to conclude the summarization part, it kind of works. It's really interesting to see that we can build a model to recreate a description or a teaser for a video just from, in our case, the text. Clearly what we want to do is integrate speech recognition and generate it from the words directly, from the spoken data directly. If we want to do this in an end-to-end model, I don't know yet. That'll be taking up all computable resources, I think. But it's very interesting to analyze the different ways of generating the summaries, to see that text tends to really pick phrases, repeat those often, and action features generate sort of boilerplate type text that's accurate if we use the RNN model. So we want to tie those together more and integrate those with the representation learning team, and sort of look at, if we train something on how-to videos, can we take it to other tasks as well and generate summaries on other data sets, not just on how-to videos. Thank you. I suggest we have questions at the end, unless there's something urgent.
Thank you, Florian. Now, to continue our theme of grounded sequence-to-sequence, we will focus on another sequence-to-sequence task, which is machine translation. And the grounded part comes from region-specific, and we'll go into that in more detail later in a while. Now, we have a picture of our team, and we have the pictures aligned to our names, so you'll probably figure out what this means in a moment. Now, so in the context of the whole project, we are interested in using English text and static images to translate it to a different language in text form. We'll start with the main question here. So, can we actually use region-specific multimodal MT to improve translation quality? So, what do I mean by that? We'll just describe it with an example. So here we have a description, and if we put it into Google to translate to Portuguese, we get this. Unfortunately, it's not quite accurate because jogador is actually a masculine form, which means it's a male player. But we can see from the image, the player on the right is female. So this shows that image information is quite important. So we have image to ground this sentence, we can probably translate it correctly. The question is, can we actually do it even better? For example, if we know that this is the region that is described by the player on the right, and we know it's female. So can we actually use this grounding to actually perform machine translation and improve it? In this case, we can translate to the correct form, the feminine form, jogadora. So our research basically aims to answer this question. Right, so for our data set, we are not using the how-to data set as in the previous groups. And this is because we found in our early experiments that the speaker who talks about things don't really talk about things that appear in the image. So whatever they say is not shown in the picture. And things they don't mention actually shown. So there are two little problems. And in our case, we want to investigate how we can use region information for machine translation. Fortunately, with that information, it's a bit sparse and it's a bit harder. So instead, we focus more on an image data set, image description data set. This is a 30,000 image descriptions with English, and it has been professionally translated to 3 different languages, German, French, and Czech. And we are using these languages in our experiments later. And we are also using these alignments available from the dataset, which are alignments of image regions corresponding to the English text. So we go through our system. It's a pipeline. So we go through one by one. First step, well, the first thing we need to do is to define what do we mean by regions and where do we get these regions. So there are 2 ways you can do around it. The first way is just to use the annotation that I mentioned earlier. So this is the Oracle regions of Go annotations. Second way is to use output of a visual detector. And in this case, it's for 545 categories. So for example, a swimming pool, or a man, or a detector for a table. So with visual detectors, of course, it can be a bit noisy, and if you detect many things, you get many false positives. And unfortunately, if you be too strict, you miss a lot of stuff. So we are trying to find the balance between precision and recall. And for our experiments, we decided to use this particular threshold as the point of the most balanced precision and recall. Okay, so now, once we have our image regions, we need to represent it somehow. So most obvious thing to do is to take a region and then crop it out and then pass it to a CNN classifier, which is trained to classify 1,000 object categories. And we extract the full 5 features from this CNN classifiers and embedding. And we can do this for each different region. Okay. One main problem with CNN embeddings is that it varies, the representation actually varies between different objects, even if it's the same type of objects. So in this example, we have region for women. These 2 women are actually women. So in a semantic sense, they are the same thing. But in a visual sense, they look quite different. So, and for attention, this is quite important. To use this region information as empty, we need things semantically more similar. So what we also experiment in our experiment is to take this word, label, woman, and then represent it as a word-to-vec embedding, as a semantic embedding instead. So now, these 2 regions will actually have the same embedding for woman. And we will also call this category embeddings in our experiments later. Right. So now that we have regions, we can actually perform our experiments. So we have 2 next steps, is actually to align regions and to perform machine translations with this alignment. So there are 2 ways to go about it. The first way is what we call implicit, where we do alignment and empty together. And the explicit method is first we perform the alignment between region and text, and I use this information for machine translation. So we go through the first step first, which is implicit. And this will be, I'll pass this to Alyssa to talk about this section.
Thank you, Josiah. So So I'm Elisa, and my work has been focused on devising algorithms to learn associations between visual and textual information in an implicit way, so mostly through attention mechanisms, and also using this grounded representation to guide machine translation. So one approach that we looked at was standard decoder attention, where you're basically grounding your representations in the target side. So at the first step, we have a CNN encoder for each of your M image regions, and an RNN encoder for your source sentence. In the encode phase, you produce a pool 5 vector for each of your regions, and also you encode all of your source tokens. And then in the decode step, you have one attention mechanism for the visual features that computes visual attention distribution, and another attention mechanism over your textual attention, which then computes your textual attention distribution. And then you use those together either through concatenation or hierarchical methods in order to produce this context vector, which is used for the decoder. And then you have regular cross-entropy loss over the translation. So we visualized the attention that was happening in this decoder model. And as you can see, well, we didn't really get any improved metrics. So we wanted to look at the attention to see what was actually going on. And some of the alignments we got, for example, with the concatenation fusion, are kind of questionable. Like, some of them make sense, and then some of them are questionable. So for example, we have a man. For some reason, it aligned it more to the region with the grass. And like, although there is part of a man in that region, it's questionable why the model decided to pay most of its attention to that last region. And then if we look later, there's a slightly better alignment. For sits in the grass, it didn't actually look at the region that corresponds to grass. But then we do get another questionable alignment where it aligns the sky with the grass. And a similar thing is happening with the hierarchical fusion. So we're mostly focusing on one region, and this region, in this case, it's the third region. And although all of the content information is in that region, you would kind of expect more of like a clear alignment to different parts of the image, into different regions for each of the text phrases. So that brings us to a different approach, where we try to ground the visual information on the source side instead of the target side, where basically you're performing your attention before you decode. So you have the same setup where you have a CNN over each of your image regions and an RNN over your source sentence, and then you encode your sources. So if you have M image regions, you have your M pool 5 vectors. And for each of your text tokens, text embeddings, you compute an attention over each of your image regions. So you get a distribution that basically shows you which word is aligned to, or for a given word, which region it's most aligned to. And you compute attention for each of the words that you have, and then you calculate these weighted word vectors. And this basically represents the text with visual context. And then you use these weighted vectors and your original text vectors from the RNN encoder as input to your decoder, which has the standard attention mechanism and it performs attention over your text and your text vectors in image context. So we also tried this supervised encoder attention model, where it's the same exact setup as from the previous slide, but we're also adding a loss over the attention. So we're really trying to push the model to align each of the content words to the proper region. And then this loss over the attention becomes an auxiliary loss in addition to your cross-entropy loss for translation. And as you can see, we get pretty exciting results for alignments. They're a lot more clear. So for example, if we go left to right on this graph, we see that man is clearly aligned to the region with the man in it. And then ball is clearly aligned to region B, which has the ball. And pink shirt is clearly aligned to the pink shirt. And grass is also aligned with the grass. And unfortunately, the metrics don't really improve, but we do see that our alignments are a lot clearer, so we can use supervised attention to produce better grounding, implicit grounding in images to textual information. And also, although our metrics don't really improve, we did want to look at the human evaluation because we clearly see that the model is doing something useful, so maybe there's something that the meteor scores aren't telling us. We'll go into that later. So now we're going to talk about a different type of way that you can ground textual information, and I'll hand it over to Joseph.
Right, so now we have seen implicit alignment between regions and MT. Now we're going to the explicit method, which is first, we need to align the region first, and then perform machine translation. So I'll talk about the third step here, which is learning the alignments between a word in the English sentence and the image region. Now, we've explored different methods to do this, and we found in the end we settled on this method, which seems to work best. So what we did was to compute sort of similarity matrix between words and concepts. And what I mean by concepts are actually detections of the objects and their labels. So in this case, we have the cat here and the dog here. So to perform our alignment, if we say we want to align the word kitten to one of these regions, what we do is to find the region with the highest similarity between the word kitten and the label of the characters. And what we did was to compute the cosine similarity between the word embedding for kitten and cat. Okay. With this method, it works surprisingly well, considering it's quite simple. So we have lady aligned to the lady. We have even white aligned to this specific white region. And we have tennis racket aligned correctly as well. And same for this, we have man and in the orange hat. Of course, in our model, we are forcing the text to be aligned to something even if it's not there. So it's got something somewhere. But of course, this is for future improvement. But for what we need now is to use this information for machine translation, so we'll keep this for future work. Right, so now that we have our regions and words aligned, so how can we use this to align and to guide NT? So I'll pass this on to, sorry, I was still Amanda, but Jasmine.
Hi, yes, I'm Jasmine, and I'm going to be talking about how we used grounded representation to guide machine translation. So after generating these explicit alignments, we wanted to use these grounded, or we used these grounded representations to further specify each of the source words with information that we got from the corresponding image regions. So for a given alignment in this image, say the alignment between the yellow pants and the blue bounding box here, we also have a detected category of what is in this image region. So here the category would be clothing. And this category that we detect is the visual information that we use to specify the source words. Another option would be to use the pool 5 feature as the visual information. However, we thought it just made more sense to supplement the learned word embedding with another word embedding, namely the pre-trained word embedding of the category. So that's why we're using categories for these experiments. There are two sets of categories that we work with. Number one being the Oracle categories, more general categories, and the second one being the predicted categories, of which we have 545. This is a graph where we have all these 545 categories. It's organized hierarchically in that near the center we have more general categories, and near the outsides we have more specific categories.
Jasmine, what is that kind of a graph called? Does it have a name?
Probably, but I don't know what it is.
Maybe flow graph, but I'm not very sure.
All right, thanks.
What's in the middle?
It looks like an iris.
So after this, we wanted to assign a category to each of the tokens in all the sentences. So what we did is we would take an annotated phrase, like the man. We would get the image that corresponds to this phrase. We would look at the category of detected from this image region, and then we would use this category as the category of the noun head of the phrase. For all the other words, we would set the category to empty. Then for each of the source words, we would take the learned word embedding, we would fuse it here with the pre-trained word embedding of the category and pass this into the encoder. The decoder over here we would just use the conditional decoder as usual with attention over the grounded text representations. So these are a few examples where we compare how the baseline model that doesn't use category information compares to the model that does use category information. So we have in the first example, an example where the category embeddings actually hurt the translation. So the goal is 5 people in winter jackets and helmets stand in the snow. The baseline is correct. Whereas with categories, it actually hurts it and says 5 people in winter clothes. This is a negative thing that may come out of using category embeddings because it might make the sentence more general or the translation more general in a case where it doesn't need to be. But also category embedding can help, which is in the second example. So the goal is a man is standing by a group of video games in a bar. The baseline changes it to a man is standing next to a group of students in a bar, which is not exactly what we were going for. But with categories, we get the correct translation because the category embedding appended onto that noun was object, not people.
I just ask why, I'm confused as to why 5 people in winter clothes, you're determining it as not as a sort of a failure.
I'm not saying
winter jackets is more specific, but they are wearing winter trousers as well. So.
Exactly, yeah, but we're just saying that the category embedding made the translation less precise, but it's still right. I agree. Yeah, and we also ran some experiments in which we dropped different parts of the source sentences in order to inspect whether these category embeddings were really making a difference. In our first experiments, we just dropped the noun heads. So as you can see, this is an example of a source sentence that we have. We would drop the 2 noun heads and replace them with a filler token. And then we compared the performance of a baseline model, which had no category information, versus a model that had category information for all of the tokens, including the tokens that were replaced with the del token. This is a second drop experiment that we had in which we actually dropped complete sentences. We dropped 20% of the source sentences by replacing all the tokens in the sentence with the token del. And we wanted to compare whether a baseline model without category information, how it would perform compared to a model that had category information for all of the tokens, including the tokens that were replaced with del. These are some examples that compare the output of the baseline model versus the model with category embeddings. Again, another example where the category embeddings actually added noise. So the goal is that a group of Asian boys is waiting for me to be grilled. The baseline gets this correct, whereas our category model says a group of Asian boys is waiting for me to be photographed. Which, yes, food photography is a thing, but that isn't exactly what we were going for here. So, yeah. And we also have an example in which embeddings help. So the goal is a Boston Terrier is running on lush green grass in front of a white fence. The baseline gets it wrong. We are not looking for a Boston cook in our translation, but with category embeddings, since our embedding is, our category is a dog, not a person, we get something a lot closer, though maybe not exactly correct. So after we conducted these experiments, we looked at the results. In the noun drop experiment, category embeddings didn't actually help. They hurt, if anything. However, with the sentence drop experiment, the meteor scores actually improved 1 to 3 points. So yeah, that was good. Lucia is going to be talking about general results.
summarizing some of our experiments. We had a lot more numbers. Of course, we won't have them all here. And these are different models. The top ones are, the ones in gray are sort of baseline, so a strong text-only model. And then a sort of state-of-the-art multimodal model where we use the entire image and we extract full 5 features for that entire image, and we use that to initialize the decoder. And these are a subset of what we tried. Encoder, the top one's attention over regions at decoding time is the first approach that Elisa talked about, and then encoder attention over regions is the second type of model Elisa talked about, and then the supervised version of that, and then finally the model that Jasmine covered using category embeddings. And as you can see, in a lot of the cases, the numbers actually go down. This is for the 3 languages that we had in our data set. And I'm only highlighting when it goes down by at least half a million point here. But in some cases it goes up. It's especially true for English Czech, where the general quality is considerably lower. It's a harder language for translation. But still, we don't see like major improvements, so to say. So we're not so happy with that. So we decided to look at other ways of evaluating the output of the models. So first we only had Meteor. In this particular case, we're looking at accuracy at translating a subset of words that are semantically ambiguous. So we have pre-selected these words. We know they have different translations in the data set. And we wanted to see if the models can get the exact correct translation, which is the one that is in the reference. So it's a very strict sort of evaluation. We're measuring exact match between the produced translation for that word and the word in the reference, the corresponding word in the reference. Here we see a slightly better picture, even though the improvement seems reasonably low here. We have quite a lot of instances for English German and English French, for example, 1,700 test instances where there are ambiguous words, so 1 or 2% improvements is a significant number of sentences there. And again, we see that happening a lot for English Czech. So we are a little bit happier here. And then if we take this as a smaller subset of this evaluation on a different test set, where we have an even smaller subset of words, where we had humans telling, yeah, this is an ambiguous word in your data set, has multiple translations, and I could only solve the ambiguity by looking at the image. So this is a real case of visually ambiguous words that can be visually disambiguated, I can say that. And in that case, we don't have results for Czech because we don't have the annotation for Czech. But we can see that one of our models, we don't have everything there. One of our models managed to get a large improvement, especially for English German there, more than 4 points in accuracy. So again, we're a little happier, but we're even happier with small-scale preliminary evaluation that we did with humans, where we had humans looking at a subset of 50 to 100 sentences produced by 2 of our promising models. So one with the attention on the encoder of regions, not the supervised version, but the unsupervised version, and one with explicit alignment followed by concatenation between the category embeddings and the word embeddings. And the proportions there mean the proportion of times that the human selected that system to be better than the others. And as you can see, the 2 multimodal systems are generally better than the text-only version. And if we are a bit tricky and just sum those proportions, then it looks a lot better. So we are a lot happier with that. And one interesting piece of feedback that we got for 2 of the languages is that in general, the text-only system, even though people didn't know which one is the text-only system when they were evaluating, seems to have more fluent output, but less of the correct content words. Just to wrap up the various things that we looked at this part of the project, text-only versus region-specific multimodal translation, generally speaking, especially according to human evaluation, the multimodal version is always better. In terms of oracle versus predicted regions, if you remember, we had these 2 variants. Also for the alignments, oracle alignments or predicted alignments through the different methods that we used. We did not show the results for all of them, but the degradation in results with the predicted regions and alignments was very small. which means on the one hand that the predictions are good enough, and on the other hand that our models seem to be very resilient to noise. In terms of representations, we played with pool 5 and category embeddings. They seem to be comparable. We like category embeddings a little bit more because it's more interpretable. And definitely Meteor or Blue or any other metric, automatic metric that we take doesn't seem to show what we want to investigate. So the performance variation seems to be very small, but when you look at the translation, especially things like what Jasmine showed you, we see that there is a lot of difference there. So other ways of evaluating translation, such as the lexical ambiguity metric, or even better, human evaluation, are definitely things that we should do more often. So we'll do more of human evaluation, of course, and we have various ideas on better ways of using both the supervised attention alignments and also the explicit alignments for translation. That's it, thank you. Any questions on this part of the presentation? Yeah.
I was thinking about the category embeddings versus your pool 5. I'm trying to figure out what might be going on. Is it that the category embeddings are taking into account how something is described rather than just what it is?
So the category embeddings are just more systematic. So if you have two things that are meant to represent similar object, then they are represented in exactly the same way. So you see more of that in a data set. If you had a much larger data set where you had many more representations of women and men and so on, then potentially you wouldn't need to resort to embeddings. But we have a 30,000 sentence and image data set. So what we think is happening is that we see more repetition if we use the embeddings of the categories rather than the full 5 features. They're just a lot more varied than.
No, but if I understood your description correctly, the category embeddings still use the pool 5 features, right? They just
It used it beforehand, but then what we end up using with the models is just one representation of the category. So, and the models that are used to generate detections have much more data to process those pool 5 features and generate a representation that is, one would say, better as a detection. Yeah.
I was thinking about the same category embedding. Does this help with disambiguation? If there are multiple senses for the same text?
This is the intuition. With the example of a male player and a female player, ideally we had this as a slide. Ideally, if we could have an embedding for woman versus an embedding for men, and in that particular case, if the detection works, we would be using an embedding for woman, and that is what is appended or concatenated or projected with the embedding that we get from the text only. Then that should help with this disambiguation. So we need to look at specific cases like gender disambiguation to see if that's actually happening, but that's the hope.
Well, I don't want to reopen an old issue that has been as long as speech recognition and machine translation, but this notion of weighted evaluation, right? But we did this in Fei Huang's thesis on named entities, because the same thing happens. Is you really don't get much of a tick in Bleu scores, but if you look at information content, and I think maybe we should revisit this issue. You know, what distorts the information the most in terms of understanding? And at the time we used entropy, but there might be more intelligent measures now to really look at that. I think it's very point well taken that you're making there in saying that just Bleu clouds the issue, that you really distort meaning when you don't really address those issues. And I think multimodal information really gets to address it, particularly those, because most of this will presumably highlight nouns, I would imagine, right?
Yes.
Because that's what you can see.
Yeah. And also our networks, in this case, the image networks that we use are trained for object classification, so they would be better at predicting.
So word sense disambiguation ought to be.
Yeah. So the lexical ambiguity metric that we used is a way in that direction. It only covers a subset of words, which are the words that are ambiguous in our data set. So it makes sense in that respect. But if you can look at that maybe together with the more general metric of fluency, that would guarantee that we're not just getting content words translated without any coherence. But I agree. Was there another question?
I had a question related to the categories and actually the deleted words. So how did this actually work? So you informed that there was a deletion, but you also told it that it was a category closing or something like that?
Yeah, so the experiments with dropping words and sentences, we kept the category embeddings there. So we wanted to say, okay, if we don't have the actual word, but we have some information about that word, which in the 545 categories, it can be very specific enough, but it's also noisy. But in the 8 category version, where the Oracle categories, it's very general. You have it's a person, it's an animal, or it's an object kind of thing. So, and we wanted to see if that would still help. And as you can see, for dropping specific words, it doesn't seem to make a huge difference. So if we don't have the category embeddings versus having the category embeddings, it seems that the model is very resilient to dropping some words. But when you actually drop the entire sentence, that makes a difference.
When you drop the entire sentence, you still have the category attached to each of the words, or only to a few of the words?
All of the words. So some of these words have empty category because they don't have any region associated to them. So these are all function words, but also some content words which are not depicted in the image. Any other questions?
I have another question that's sort of more to all the talks we've seen so far with multimodal, which is most of them in Miao's thesis, for example, I thought it was, or some of the work that was shown here, it's clear that you get sort of high-level features that are relatively static, but that I'm not sure, and again, I'm wondering whether you do have a good modeling of action sequences or a kind of a narrative that is in the visual information, right? I mean, if I'm turning a bolt to the right versus I'm lifting a book, these are all actions that should be represented and have implication on what language says, as opposed to it's outside, the whole video is outside, or there's a lot of noise in the kitchen, which is sort of more a static feature across the whole region. And that I would imagine call for much more of a modeling of a narrative in the both visual story and the acoustic story before you in fact begin merging it.
Yeah, that's true. We haven't addressed that to a large extent. We started at least by taking, for the summarization and the ASR and spoken language translation teams, we actually looked at various frames and treated them as a set of, or even a sequence of frames with the RNNs. And that's a sort of starting point, but it's definitely not as much as we should be doing and can do. And that's one of the motivations of using videos rather than using static images. So we definitely want to do more on that.
Okay,
so we should have the break now?
Yeah, let's take a 10-minute break. I'm told that our coffee and juices have been replenished, so there should be more caffeine and sugar to keep us going. So let's do a 10-minute break and resume at 3:40. So those online, please take a 10-minute break yourself. Right, guys, let's get back together. We have 2 more interesting sections and then 1 concluding section to go. So let's settle back in. Right, who all still back there? So Harish, guys, let's come back in. Takaaki, let's get back in here. Guys, let's settle down.
You have to ask Martin specifically.
Who? Oh, Michael.
Martin.
Oh, Martin. Okay, all right. So Yanda wants me to call Martin back in. All right. All right. Let's settle back in. And Lucia, who's doing the next part? Is it Pranav? You're up. Okay. All right. Pranav, you have the floor. Please start.
So, hi everybody. For the next section, so our sub-team with Nils, Shruti and I, we looked at multi-view learning. So the big picture is we try to use representations that we are obtaining from some pre-trained models, and we are trying to see if we can sort of get some structure which is implicit in these pre-trained representations. To do this, we sort of approach using multi-view learning as our setup. So again, to sort of look at why we did this, if you look at our data set, we have speech, we have videos, we have transcripts in English and Portuguese, we have some kind of a summary. So in some ways, these are aligned, they have similar kind of information content, and we really want to make use of this. So we asked this question, what could explicit representation learning give us? Especially, in our case, we have different views. In some way, each view is different, but the information content is somewhat similar. We have visual, auditory, and language views, which are aligned. We have different kinds of things. We have views in the same modality. We have views in multiple modalities. So think of views in the same modality as text, where you have English and Portuguese. We have views in multiple modalities. We have speech, we have text, we have some vision, some video kind of representations. And also we have sort of a gradient of the representation. So we have unit level and sequence level representations. So these are all the information that we can obtain from our data set. And we were really excited to sort of exploit multi-view learning to see what can we get from that. In terms of multi-view learning, we are really interested in canonical correlation analysis, which is one kind of setup where we can do multi-view learning. This is sort of a toy example to sort of illustrate what canonical correlation analysis can give you. So typically, we have task-specific representations that we obtain from a model that was trained for a particular task. In the above case, say a task of action recognition, we have these representations. Here we have, say, the task of machine translation, so we have representations on English and Portuguese. So that's English and Portuguese. For some reason, the R, it's RI, it's real with images, it's real over English space, and say this is Portuguese space. So we have these representations that we obtain from pre-trained models. These were not trained for the task of machine translation, say, or they are trained for machine translation, but we just obtain these representations. And then we ask, these are aligned. So probably there is some hidden or latent information which is sort of structurally common. And then can we obtain this? So using CCA, what CCA does is it takes the initial representations and we learn transformations where the projection of the initial representation is in the common shared space highly correlated. So somewhat very close to each other. So the representation over there in the task specific, say the video one, is very close to one of these texts which sort of represents, say, the tire over there, and sort of the Portuguese version of tire. All these are highly correlated, very close to each other. So in a nutshell, the simplest version of CCA, which is a linear CCA, is that you take information, say the representations in X, which is, say, view 1, view 2 is, say, language view, we have representations of that, And then what we are really interested in is obtaining these transformations, U and V, where the projections, so U transpose F theta of x is the representation of x, and V transpose of G phi of y, which is a representation of y, are highly correlated. That's our objective. Now, why we are interested in this is because this is very elegant in some ways, and it has a closed form solution. So algebraically, it has a closed form solution. We also explore extensions. So especially we are interested in extending this to multiple views. So I showed 2 views. We can actually extend to multiple views. So if we do that, there is a slightly different objective. But again, the concept is obtaining these transformations where the projections are highly correlated in the shared space. So that's what we want. And this is known as the generalized CCA. We are also interested in a bleeding edge sort of research which came out of JHU, where we are interested in deep generalized CCA, where it's almost the same thing. It's just that instead of having the initial representation and then do a CCA over that or obtain transformations, we first learn a particular nonlinear space where the projections, where we learn the projections over these nonlinear representations, which we learn, such that the projections are highly correlated in the shared space. So we are really keen on exploring CCA and the versions of CCA in this sub-project, especially because these are the properties that we are looking at. So CCA helps us obtain maximally correlated information that is consistent in some sense with each view. It sort of gives us the handle on the amount of covariance, variance shared in each view. It also allows another way of grounding the information that is consistent with each view. We are basically using representations that we obtained from pre-trained models. But again, what we are considering is the projections are somehow consistent with other views. So in some ways, it also helps us denoising. Structurally sort of information which is not consistent in both views, so thereby denoising and then retaining the maximally mutual information content. So our project sort of looked at these things. First, we start with linear CCA and start exploring the deep versions and the deep generalized versions. And we start from text views and go on adding modalities. To take you forward in this journey of exploration, Nils and Shruti will take on with the other kinds of experiments.
Hey, I'm Niels. So we started with a very simple experiment. So here we're looking at word embeddings. And our view number 1 was an English word, or view number 2 was a Portuguese word. Each word is represented by its word embedding. We picked that word embedding from a trained MT system. So we learn CCA-based representations on top of those word embeddings. So we're refining the word embeddings. How do we evaluate those? So we're going to take all the English words that we have and project them into a shared space with the learned projection. And then we're going to take one Portuguese word at a time, project it into the shared space, looks for its closest neighbors, its closest English word neighbors, and then we're going to check whether its translation is within the first 10 neighbors or something. So that's what we call recall at 10. If we match the words just based on their frequency, we get a low recall, like 0.1%. And then the best CCA method that we have gets 20.7% recall. So to give you a better intuition of what's happening, on the left here is what the nearest neighbors look like if you don't do anything to the space. So you just match the initial English word embeddings with the Portuguese embeddings, nothing special happens. And then CCA warps the space and gives it a semantically meaningful structure. Okay, so after words, we moved on to sentences. And so we needed representations for sentences. We took something simple. We're using trained machine translation models. We encode each sentence with the encoder, and then we mean pool the output of the encoder. And that's the yellow thing. That's the yellow shape. That's our fixed size embedding for a sentence. And then on top of that, we learn our CCA projection. So one view is the English sentence, the other view is the Portuguese translation of that sentence. And again, we evaluate it by projecting all of the English into the shared space, projecting each Portuguese sentence, and retrieving the 10 closest English sentences. So in that setup, we actually have a very high recall, 81% with linear CCA, 95% with deep CCA. And this recall is over a test set, which means the model has absolutely not seen these sentences, but it's actually able to pick out the correct translation every time. We wanted to be sure whether, so these sentence embeddings were actually learned by mapping English text to Portuguese text or vice versa, so they sort of contain some kind of bilingual information. So we wanted to see if that would still work if we had a different base representation.
So just a quick question about the evaluation. So the correct translation was always in the test set?
It is in the test set.
So if the test set only had size 1 or 2, this would be, it'd be very easy,
right.
100% recall. And how big was the test set?
2,361 examples. So if random, if you picked a random sentence, you get 0.04% retrieval.
Right, and if you pick 10 random sentences, it would be 10.
That's yeah. Oh, a bit more.
Recall it.
Yeah. Yes, thanks. Okay, so we tried a different kind of representation. So in that case, we're using word embeddings that were learned on a single language, so it doesn't have any information about anything but the source language. We mean pool them and project it following a method that was published last year. And so use that as our sentence embedding. Again, we train CCA on top of paired views. And we still have a very high recall, so 97% for linear CCA, 96% for deep CCA. So that's nice, it works even when you change those initial representations. So after this work with sentences, we wanted to add another modality. We wanted to add video representations. So we had to embed, we had to pick a representation for a video. So again, we picked something simple. We classify each frame of the video using a ResNet. So we get a 1,000 dimensional vector. Each dimension tells us whether or not that specific class is present in the image. So it's a posterior. We average the posteriors over the entire video, and that's a fixed size representation, which we're going to call bag of classes for short. This is one of the representations we use. We also tried other things on videos, but I'm only going to talk about this. So our two views are English text and our bag of class representation of the video. In that case, we had a very low recall at 10, actually. We hypothesized that the bag of classes is not that reliable in general. So that's probably what happened. So here's a summary of our results with text, where one view is text. So with words, we had a decent recall, 21%. Sentence to sentence retrieval was very high, in the high 90s. With images, it was very low. So based on those results, we wanted to see if we could use our sentence representations, so the projections of the sentence representations, and also the projections of the words in an NT system. And wanted to see if that would make a difference and hopefully improve some of the blue scores. Okay, so since we had a very high recall, we did this simple experiment which doesn't involve learning any model. So we take a Portuguese set of sentences. So let's say we're going to take just the training set. We map it to the shared space, and then we take our English test set, and we want to translate each English sentence into Portuguese. So we project each sentence into the shared space, look for the closest sentence in our reference set, and use that as our translation. So if we use only the train set, we get a blue score of 5. There's many reasons why we would only get a very low blue score. For example, maybe there simply is no sentence in the train set that's appropriate to translate a sentence of the dev set. So we did this other experiment where we pick it randomly and we get 0.4 blue. So the model is doing something, but maybe it can't do that much. When we add, if we add the actual gold transcriptions of the test set into that reference set, so now the reference set is train plus test, then the blue score goes up to 80, which means that the model is able to pick out the correct sentence in this larger set of sentences. So to compare, the number of sentences in the train is 185,000, and the number of sentences in the test is 2,000. So you would expect that it would drown out the information, but it didn't. Okay. So another retrieval-based evaluation we did is we have a trained MT system that goes from English to Portuguese, and we pick the 10 best hypotheses, so the 10 best list, the 10 best hypotheses of Portuguese sentences given a source English sentence. we project all our 10 best sentences into the shared space, project the source sentence, and then pick the closest one and use that as our translation. So we did this exact experiment. 92.7% of the translations change as compared to when we don't do that. So something is happening. We're changing the output of the NT system. But this was actually not reflected at all in the blue and meteor score. So this means that it would make sense to include this projection somewhere in the beam search. It would probably make a bigger difference.
Can you go
Yes.
back for a second?
Yep.
So from these 10 best sentences, if you picked the one that had the best, I guess, sentence blue or something, do you know how much better you'd get? In other words, what's your room for improvement?
Good question.
Right. Yeah, we haven't done the Oracle yet. So, okay, I get your question, but
Right, because if the room for improvement is only 0.5, then, you know, it's not much. But if it's 5 points, it's from 53, you can go to 59, then hey, then this isn't getting any of it.
right. Yeah, that's
Because it's clear that if you inserted the reference translation as the 11th choice, your model will probably pick it up.
Yeah.
So the question is, how good are the choices?
Right.
Okay, so next experiment, we tried to actually use the CCA projection inside the machine translation system. So here we are so we're simply concatenating the word embedding that we learned into the machine translation system. So it has access to the projected word embedding. So when we do this in the sequence-to-sequence model, the training changes a bit, but the final blue score doesn't really change that much. Okay, we did other experiments, but now it's more interesting to move on to speech, so I'm going to hand it over to Shruti, who's going to tell you about this.
Thank you, Nils. So to recap the goal of our project, we've looked at text-based models for multi-view learning, but following the curve that we have, let's move on to speech-based experiments. So before we do that, let's look at how we extract these representations that we use from a speech model. So our speech model is a sequence-to-sequence model, but instead of training it towards characters, we train it towards words so that the representations learned are comparable with the machine translation model. So we trained a word-based speech recognizer that has a vocabulary of close to 19,000 words. And it performs well as well compared to character models. Then with these models, we mean pool over the context vectors to get a single sentence representation, which we also call the bag of audio words. This is what we'll use in our future experiments now. The first experiment we start with is using speech as one view and the text representations as another view. So both of these views are from pre-trained speech recognizers and machine translations, trained independently, but we hope that via CCA we will be able to obtain a correlated vector that is able to use the related information from both of these inputs. So to evaluate this model in the same way like we evaluated our other models, we calculate recall at 10 over the test set on the linear CCA and the deep CCA. And we see that if we try to do the task of retrieving text given a speech segment, which is like ASR, we get a very nice recall score. If we go the other way around, where we want to retrieve speech given text, the task is harder here, but we still get a high score. So the model is able to pick the correct speech segment given text from the entire test set. The next experiment we try is with speech and video features. We did a similar experiment with text and video where it did not perform well, but we expected this model to perform worse than that because the input is a tougher set instead of text. But the results don't change much. So we can say that it is possible that the video representations we have are not really correlated with either text or speech, and the model is not able to capture any similarities here.
And this is the final model that we train, where we have all the parallel data available and we train a single generalized CCA model with it. We have the speech input, we have the English text, we have the Portuguese text, and the video representations. So to evaluate this, we do a similar cross retrieval. This grid shows input on the y-axis and different modalities on the x-axis. So if we retrieve English text given speech, we get a high score. If we retrieve Portuguese text given English speech, we still retrieve a high score. This task is something similar to spoken language translation now. And video representations are still bad. So the thing to note here is that we've trained a single model with all these different modalities, and we are doing cross-view retrieval here on the test set. To compare the different models we have so far on a single task of retrieving text given speech, if we do only speech and text, we get a recall of 90%. If we add in all the other modalities we have, the recall drops, but we are able to do more tasks like translation, text translation or speech translation, and the drop in performance on the recall is not that much, so it's a good trade-off. Another way to evaluate these models apart from recall at 10 would be word error rate, like how we did for text with blue. So the task here is to retrieve a text segment given a speech segment. We take the one best output and consider that as the new hypothesis and calculate the word error rate over the reference. So although we picked the one best sentence here, the evaluation is still at a word level. So the baseline or the sequence-to-sequence model here that we saw before gives a word error rate of 24%. This is on the 300-hour set of the how-to data. If we pick the new hypothesis only from the training set, we get a word error rate of 134%, which is as expected but a bit too high. Then if we merge the train and the test set, like we did in the case with the text examples, we get somewhat closer to the sequence-to-sequence model, but it's still a bit worse. But the fact that we are just retrieving a text segment from speech without training any model here, and it still reaches close to a sequence-to-sequence model is quite interesting. If we do a same sort of analysis for spoken language translation, where we are now evaluating for blue, the sequence-to-sequence model performs, gives a blue score of about 28. The train set again gives a low blue score, but train plus test gives something that is worse than blue, like similar to speech, but it's still close to the baseline. So with these representations that we learned, we looked at integrating them into a speech recognizer to get some sort of multimodal ASR. The first adaptation we tried was to use these CCA representations right before softmax, because these are learned at a word level, and these would have more potential to influence the decision of the softmax. But it did not go that way. The sequence-to-sequence model gave 24%, but this one gave 25%. The interesting thing was that only the substitutions increased by about 7%, but this needs more understanding of what's happening. Another adaptation strategy we tried was to include these CCA representations in the input itself, because if the decoder is not performing well with these, it might be because the representations are still rich in the speech sense. So we concatenated these learned representations at every frame in the input, but that led to even worse results. Although these models aren't improving absolutely on the word error rate, we have more models training, but we need to figure out why not, and maybe these adaptation strategies are not the best way to include these. So in conclusion, in our project, we implemented and explored various different generalized deep CCA models. One of the interesting things we saw is that CCA can learn strong representations with high cross-view retrieval scores with a simple closed-form linear version as well. And we are looking at exploring further integration strategies for task-specific models. Thank you.
We have time for questions.
I have a comment rather than a question, which is that, again, because you're looking at, like, representations rather than just measure blue score by either having the reference translation there or not, it might make sense again to focus on content words. Like, I think Lucia had this idea with ambiguous words whose translations are ambiguous. Something like that, you might reveal something about these embeddings through that to say, yes, they're putting you in the right space. So if the model was contemplating those two choices, it will make the right choice, as opposed to a whole sentence level metric which may or may not reveal what these things are doing.
True. Yeah, we agree. I mean, we just took this because we could compare then to a sequence-to-sequence baseline.
Yeah.
Because otherwise we have to do the same evaluation over there.
And particularly with the speech, for example, right?
Yeah.
Just giving it the speech signal and saying pick a sentence and speaking something with a blue score of 20. It means it's somewhere in the right, maybe not the right ballpark with the same city.
Yeah.
Thanks.
Thanks, Rudy. This is the final presentation of the afternoon, so thank you for making it this far. This is the multitask learning group. This was joint work between Amanda, myself, Loic, and Carl. And the big picture of our overall project was how could we take advantage of all of these different signals in order to perhaps produce better speech recognition results or better video summarization results. In our group, we had a slightly different big picture, which was based around all of the different tasks people were performing. And we saw some really great results from all of these different tasks. However, we think about it in terms of what are the connections between the inputs in the different tasks and what are those relationships to the outputs of different tasks. And more importantly, where could we see opportunities to share representations at the input level or at the output level? And the main question that we tried to answer in all of our work was how and when is it useful to learn a shared representation between different modalities? So before we try to answer this question, we want to define what it might mean to be useful multitask learning. And this chart will come back again at the end. Mainly, we're thinking about if we have a primary task, do we have a relative improvement or decrease in performance if we perform multitask learning? And the same for our auxiliary tasks. Do we improve or decrease performance relative to what we started with? Now, I'd love to tell you that all of our stories belong in the top quadrant here, where everything worked out. But for those of you who've done multitask learning yourself, you might agree that the harsh reality is sometimes more realistic. We're going to tell you a series of stories that range from one range to somewhere above the middle. That's as honest as we can be. And in terms of the when, we're going to look at when we maybe share the encoder between different tasks. So when we combine video reconstruction and video summarization, we have a shared video encoder on the left-hand side, which is being used to either reconstruct the video inputs or to produce the summaries that we saw earlier from the summarization team. We also look at sharing a decoder in a similar manner to the spoken language translation team, where we have either a speech or an English encoder as the input, but a shared Portuguese translation model on the target side? Is it useful to share this decoder across different encoders? We also look at a situation where we share video encoders and speech encoders for the task of producing the closed captions or the transcripts. This seems like a natural candidate for multitask learning, since the speech is the part that's missing in the video, and the video may support what's missing in the speech. We can also look at combining automatic speech recognition and machine translation, where once again we have a shared decoder producing the English transcripts over a speech encoder or a Portuguese translation encoder. And finally, our most masochistic task is doing video-based closed captioning, where you don't have any speech data and you try to produce the output that the person is supposed to be saying. And in our case, a lot of our videos do not show people speaking. It's focused on people painting or chopping vegetables to prepare an omelette. So an extremely complex lip-reading based model will fail in the majority of these cases. At least this is our expectation. But if we can combine this with a Portuguese translation model and learn a better English language decoder, can we produce better video closed captioning outputs? In the remainder of this talk, Carl will tell you about the how of what we did, and Amanda will take you through our results.
Thanks, Desmond. So yeah, as we said, we want to focus on the question of how and when having shared representations is useful for multitask learning. And I'm going to talk about the how, which means model architecture. So the question is, how do we actually want to combine the signals that we have from the different modalities together? And so I'm going to discuss 3 model types that we thought about. So as you saw in the slides that Desmond presented, we think of our tasks as a series of encoders as seen here. So we have a video encoder, a speech encoder, and a text encoder. And the simplest thing that we tried to do was use a scheduling regime where for any particular batch we pick one or a subset of these encoders and then take directly that output and feed it into our attentional decoders. So for a particular task, you might want to do video to closed captioning, and yeah, so we would take our particular batch, we would sample one encoder, and then for the next batch, do a different one, and so on, and cycle through it as so. However, there's some shortcomings with this model. The thing is, because we're sampling from different tasks and the difficulty of them varies a lot, you have wildly different losses in several situations. And also, it doesn't really help our decoder that it's getting different inputs from our encoder encodings. And so we'd like to think about a different kind of way that makes this more conducive. And so we proposed having this intermediate layer, this Z space that we're calling it, and the idea here is because all of our data and all of our models are sequence to sequence, we use a sequential intermediate step. So what we do is for each of our encoders, we have an attention mechanism over all the hidden states, and then we sum those together into all those context vectors and feed that as the initialization for our intermediate Z, R, and N. And then we do this recurring step for a fixed number of steps, and then using those states, we do attention over those to proceed to decode. And this is an idea that comes from Liu et al., which was traditionally used for machine translation only, but we wanted to extend this to see if it would work with multiple modalities. Another idea that we had, which doesn't use an intermediate shared space, is something we're calling mutual projection networks. And this assumes that we have at least 3 modalities of aligned data, which we do. And so given our data set, we sample a primary encoder X, a primary decoder Y, and an auxiliary encoder A that is not used for our primary task. And so to compute the loss, we do our regular log probability loss for our primary task going from X to Y. We also add in this additional term here, which is where we project the hidden states of our primary encoder X and our auxiliary encoder A, and try to minimize the distance between these projections, and try to do the same for our primary decoder hidden states Y and our auxiliary hidden states. And that distance is actually a max margin objective where we take contrastive examples in our batch and try to minimize the distance between the similar ones. And use cosine distance to measure the difference between the mean pool of those hidden states. So here's another way of looking at that. You see between X and Y we have our primary task, and then we have our auxiliary encoder, which is not actually used in decoding. It's used kind of as a regularizer between our different modalities. So that's those G terms there, where we try to regularize the hidden states of our encoders and with the decoder by projecting them into this space. And so to give an example with an illustration, we have here the task of ASR going from speech to text. So our speech encoder is X and our English decoder is Y. And then we like to throw in a video encoder, so we have this ResNet video encoder, and we have these pool 5 features that we project and mean pool, and we do the same with our speech encoder hidden states and try to minimize that cosine distance. And then we do the same thing with our auxiliary hidden states and the English decoder hidden states. And so now Amanda is going to talk about some experiments that we did using these 3 different models.
Thanks, Phil.
Hello everyone. So now let's take a look in our exciting experiments, or not so exciting results. But so first, what I want to highlight here is that we used, for all the experiments that I'm going to be talking about today, we used the same hyperparameters for all the models, and also the same data preprocessing pipeline for all the experiments. And the models that we're going to be comparing to here is the single task model, that's our baseline, and the 3 multitask learning models that Carl just explained to us. The multitask learning using the scheduling, the multitask learning using the shared recurrent space, and the multitask learning using the mutual projection network. So our hypothesis for these experiments is that the multitask learning models will outperform the single task models because their representations need to be useful for more than one task. So let's see what we have. So in the case when we have a shared encoder for the video reconstruction and the video teaser generation, our results look like this. So you might thinking that we don't have a good result using multitask learning, but actually these results here are just very good. We have another very hard task here that is to fit everything into memory. So unfortunately, we couldn't get results for these experiments, but we are trying to figure out this problem around these experiments, and we are gonna let you know when we have these results. So here, when we have the shared decoder for spoken language translation and machine translation, we got these results. So in the left side, you can see the results for the spoken language translation from English speech to Portuguese text. You can see that we got improvements for this using task learning and just using the scheduling and using the MPN. But on the other hand, for the auxiliary task, which is machine translation here from English to Portuguese, our performance decreased a little bit when we use multitask learning. So, oh, and also, sorry, I forgot to mention that we can also see that this is a very hard task for the shared space, for the recurrent shared space.
Can I ask you something?
Sure.
So, just, yeah, when the improvement in the primary task is larger, the degradation in the auxiliary task is also smaller.
Yes.
So that means something must be going right.
Yeah. This is what we think.
Even in the auxiliary, it's not big. So do you have a sense?
Yeah, they are proportional. We are investigating this, but we don't have an answer right now.
All right.
This is for next week.
For next week, okay.
So, our conclusion for this experiment is that it's a very, it goes into the harsh reality for the shared recurrent space. We got some improvements for the primary task, but unfortunately, our auxiliary task got decreased a little bit in the performance. So the other experiment is when we used to have a shared decoder, but now for the automatic speech recognition and video closed captioning. And so in the left graph, you can see the results for the English ASR, where we compute the word error rate, where the lower is better. We can see in the right side the results for the video closed captioning, where we compute the blue score over the whole paragraph, where the higher is better. And we can see that in this case we didn't have improvements using multitask learning. So in this case, this is what we like to call our nightmare mode. It's a very hard task, and unfortunately we couldn't have improvements using multitask learning. So another case when we have shared decoder, but now for ASR and NP. So in the left you can see the results for ASR using English, where we compute the word error rate again, and lowers is better. And the other side, we show the results for machine translation from Portuguese to English, and we compute the blue, where higher is better. We can see that here we had we have a little bit of improvement in the machine translation, but we don't have that much improvement in the ASR. So our conclusion here for this experiment, it's again a harsh reality for the recurrent shared space. We have some improvements using MTL, but we have mixed results using applying the MPN. And here another experiment is again using the shared decoder, but for video closed captioning and machine translation. Again, a very hard task. We could show that we got some improvements in the video closed captioning, and but on the other hand, for the machine translation, our performance decreased. So our conclusion for this experiment is that we got improvements for the primary one, but unfortunately, again, our performance for the auxiliary task decreased. So now Luis is gonna wrap up and do a summary of our.
Thank you, Amanda. So if you go back to our initial plan, when we hope to be on the top right part, and we try to place our task combination results based on the result that we got. Of course, we couldn't make an extensive search from this space, okay, different combination, but we might have some kind of insight. Okay, so first of all, if we look at this very difficult task of video closed captioning, I remind you it's just trying to transcribe a video without having the speech, which is sounds like crazy, right? When the experiments showed that we could get a slight improvement, we have to be careful with this kind of improvement because the scores are really, really low, okay? But we might think that the language model at the decoder part is being helped by the auxiliary task. But in this case, the auxiliary task is a bit decreased. The performances are decreased. Okay, so we still consider that it's a kind of win in this case, but further experiments have to be done. Then we have two tasks which are somehow related. Okay, so it's trying to use MT to help from going to speech transcription, okay, ASR, and speech translation, SLT. So we can see here that we have some few improvements on the main task. So the SLT on the ASR have some kind of slight improvement here, okay, and one with at the expense of the auxiliary performances. While for the ASR, then we can have a very tight, very slight improvement for both of the tasks. These are still our tasks, and we argue in this case that this is helped by the fact that all the modalities in this setup have a kind of semantic parallelism. So what we mean by semantic parallelism is that in the Portuguese text, in the English text, and in the acoustic signal, they are all the same kind. They are all saying what is being said, right? Whereas for the video closed captioning, actually the video contains what is going on, which is very different from what is said, for the reason that Desmond explained earlier. Okay, and as for the nightmare task, combining ASR and video closed captioning, basically the problem here is that the decoder can't cope with two very different signals: the video showing what's going on and the speech mentioning what is said. Okay, and in this case, the signals are really different, and the model cannot really deal with it. Of course, these experiments are based on a few experiments that we did. If you remember, the experiments about the recurrency space, which provide lowest results, are really the first tries, and of course, more investigation have to be done for this. So, what did we learn? What can we conclude about those 6 weeks? So we explored different multitask learning schemes, okay, with different models, and we are pretty proud of them. Okay, so the scheduling, the shared space, which was first applied to multimodal inputs, and the mutual projection network, which is a new idea, which we still think they are sound, but we need more time to perform more detailed analysis and more detailed inspection of what is really going on. Okay, are we learning something? We couldn't look at the representation themselves. Okay, we had an extrinsic evaluation looking at the blue scores, looking at the word error rate, which might not convey the good information for this type of combination. Okay, and all what we did asked the question of whether we can cram multiple modalities into a sequence of vectors. I'm thinking about the shared space here. In all experiments we performed, it happened that no, we cannot for now. Okay, but does this mean that we should stop doing this? Probably not. Okay, this is just a start, and we really want and really need for an exploration of different architectures. As for the mutual projection networks, okay, this kind of regularization, we have some experiments running, show that the auxiliary task, which is used to help the encoders and the decoders, tend to regularize the networks pretty nicely. The improvements are still slight, but I think for a new method which has been developed within the last 3 weeks, I think it's really a nice idea, nice result so far, which really needs more investigation. And we will be pleased to do that probably in the future. And that's all. Any question for the multitask learning group?
Remark, but I'll wait till others ask.
Jan?
Yeah, you said you played with scheduling. So what did you do for the multitask model you presented? Was it like just training? What did you use there? Your results and all of that?
So all the MTL results are with scheduling, and so there's no combination because we select only one encoder at a time. Okay, so we don't need it. The only things which is needed is that the encoders at some point are mapped to the same dimension, and then the decoders receive sequences of.
Yeah, but do you like switch the task or like do you have a special schedule? Yeah, but just like randomly shift or like one.
So we have some manual scheduling where you design a sequence of tasks with a frequency, and then it just loop over it epoch after epoch. Okay, and we developed some random selection, but we didn't apply them here. We did a lot of experiments, and manual scheduling was pretty good. And the ASR team did that with sampling 70% or 50%, and basically you can reproduce similar trend with manual scheduling. So we stick with it.
I think I'll hold my comments because I realize we're running over, so we should just conclude.
Okay, I'm just putting it. Thank you.
This is a one-slide wrap-up of the whole thing. You've seen conclusions for the individual sections of the project. And for this one, we limited ourselves to one take-home message per section. So I'm just going to read them to you. First take-home message is that multimodal ASR can also work with the sequence-to-sequence models. We had promising results for spoken language translation and ASR. Summarization or teaser generation works surprisingly well, but we do need a better way of evaluating those teasers or summaries. Region-specific multimodal MT makes sense with the right evaluation metric, so that again, canonical correlation analysis can obtain rich representations from various views and modalities, and multitask learning can be useful, and the potential gains will be proportional to the semantic relatedness of the different signals that are being combined. So I think we can say that after 6 weeks, at least compared to when we started, we are, we need to keep trying. We are pretty grounded, but not all the time. Thanks, Yenda, again for the animation. Oh, we have some, sorry, I should not forget that. That's important.
We'll just watch this whole thing.
Yes, it's a 1 hour GIF animation each episode with it. Just a big thank you to all our institutions, our funders and projects, and also special thank you to Christian Khudanpur from Facebook, who helped us a lot in the beginning of the project, but could not be involved during the actual 6 weeks. Thank you.
Okay, if there are any last comments to either the second team or even the first one? Does anyone have any energy left? I do. Right. Well, if there are no further questions, let's call today's proceedings to a close, and we will resume again tomorrow morning, bright and early. Breakfast at 8:30, and presentations start at 9. For tonight, all of you are on your own for dinner, so please take advantage of this nice gathering. Find people you haven't talked to in a while and go get dinner somewhere nearby. And we will see you all tomorrow morning.